By the early 19th century, human mobility was constrained by technologies that had changed little for centuries. On roads, people depended primarily on horses, carts, and carriages. These systems were familiar and functional, but they imposed clear limits. Speed was modest, endurance depended on animal health, and range required frequent stops for rest, water, and feed. Travel schedules were unpredictable, influenced by weather, terrain, and the condition of animals rather than by human planning alone. Urban centers felt these limitations most sharply. As cities expanded, the number of horses required for transport increased dramatically. Streets became congested and unsanitary, filled with animal waste and noise. Maintaining large horse populations demanded land, labor, and continuous expense. For individuals and businesses alike, mobility was costly and inefficient. Travel beyond short distances remained slow, while daily movement within cities grew increasingly burdensome. Railways offered a partial solution. Trains dramatically improved long-distance travel and freight movement, connecting cities and industrial hubs. However, rail transport was fixed to tracks and schedules. It solved the problem of distance, but not the problem of flexibility. Passengers still relied on horses or walking to reach stations, and goods required multiple transfers. Personal mobility, moving independently, directly, and on demand, remained out of reach. These constraints shaped economic and social life. Business decisions were delayed by travel time. Access to markets and services depended heavily on location. Personal freedom of movement was limited by infrastructure rather than choice. The problem was not merely speed, it was autonomy. A new form of transport was needed, one that could operate independently of animals and rails, offering consistent, controllable movement wherever roads existed. The Industrial Revolution intensified existing mobility problems. Factories increased production, cities expanded rapidly, and populations became more mobile in search of work and opportunity. Goods needed to move efficiently between workshops, warehouses, markets, and ports. People needed to commute, coordinate, and travel with greater frequency. The demand for movement grew faster than the capacity of traditional transport systems. Mechanization transformed manufacturing, but transportation lagged behind. Machines powered by steam and later by combustion engines revolutionized production, yet road travel still relied on animal power. This imbalance became increasingly apparent. Industry could produce faster than people and goods could move on roads. The efficiency gains achieved inside factories were lost outside them. Railways again played a critical role, but their limitations became clearer as well. They were excellent for bulk transport over long distances, but unsuitable for individualized travel. They required centralized planning, fixed routes, and significant capital investment. Rural areas and smaller towns often remained poorly connected. Even within cities, rail networks could not provide door-to-door access. The pressure for a new solution came from everyday needs rather than theoretical ambition. Merchants wanted faster deliveries. Doctors needed reliable transport for emergencies. Craftsmen and professionals required mobility independent of schedules. Individuals increasingly valued personal freedom of movement. The conditions were forming for a technological shift. A machine capable of converting stored energy into controlled motion on ordinary roads, without reliance on animals or rails. The idea of a self-propelled road vehicle challenged long-standing assumptions. While steam engines had powered trains and ships, adapting them to road use proved difficult. Steam vehicles were heavy, slow to start, and required constant attention to pressure and fuel. Early experiments existed, but they were impractical for everyday personal transport. The internal combustion engine presented a different possibility. By igniting fuel directly within the engine cylinder, it could produce power more efficiently and with less bulk than steam systems. However, this technology was still immature in the mid-19th century. Engines were unreliable, noisy, and poorly understood. many engineers doubted their suitability for transportation, especially on uneven roads. Skepticism extended beyond engineering concerns. Roads were designed for animal traffic, not machines. Regulations often restricted mechanical vehicles. Public perception favored familiar modes of travel. A self-propelled carriage appeared unnecessary, even disruptive. The prevailing belief was that existing systems, horses for roads, trains for distance, were sufficient, yet the logic of mechanical mobility was compelling. A machine did not tire, require feeding, or suffer from illness. Its performance could be standardized and improved through engineering rather than breeding. If an engine could be made compact, controllable, and reliable, it could offer unprecedented independence. The challenge was not to modify existing vehicles, but to rethink road transport entirely around mechanical power. When the first practical automobiles appeared, they were met with curiosity rather than immediate enthusiasm. Early vehicles were slow, mechanically fragile, and unfamiliar. Operating them required technical knowledge, and infrastructure was minimal. Roads were poorly suited, fuel availability limited, and maintenance complex. Adoption was gradual, not sudden. However, the advantages became evident with use. Automobiles offered direct, point-to-point travel without dependence on animals or fixed schedules. They operated when needed, where needed. Over time, engineering improvements increased reliability, speed, and comfort. As production methods improved, costs gradually declined, making automobiles accessible to a wider population. The transformation extended beyond transportation itself. Cities adapted to accommodate vehicles, reshaping streets, commerce, and daily routines. Industries emerged to support automobile production, fueling economic growth. Personal mobility altered social patterns, expanding access to work, education, and leisure. Distance became less restrictive, redefining how people organized their lives. The ultimate success of the automobile lay in its alignment with human needs. It addressed a practical problem, independent mobility, using a scalable technological solution. By replacing animal power with mechanical power on ordinary roads, the automobile bridged the gap between industrial capability and everyday life. Its impact was cumulative rather than immediate, but once established, it became foundational to modern society. The automobile did not succeed because it was novel, but because it solved persistent limitations in transportation with clarity and efficiency. It transformed roads into pathways of personal freedom, setting the stage for one of the most influential technological shifts in history. Karl Benz was born on November 25, 1844, in Karlsruhe, in what is now Germany. His early life was shaped decisively by his family background and by loss at a young age. His father, Johann Georg Benz, was a locomotive driver, an occupation that placed him directly within the world of mechanical power and industrial progress. Steam engines, railways, and precision machinery were not abstract ideas in the Benz household. They were part of daily reality. This influence was cut short when Karl was only 2 years old. His father died from pneumonia, leaving Karl to be raised primarily by his mother, Josephine Benz. The loss had lasting consequences. Josephine became deeply committed to securing her son's education, believing that technical knowledge and discipline were the best forms of security in a rapidly industrializing society. Her determination would later prove essential to Karl's development. From an early age, Karl showed an unusual aptitude for technical thinking. He was fascinated by machines and mechanisms, often studying how objects worked rather than simply using them. His interest aligned naturally with the industrial environment of mid-19th century Germany, where engineering and applied science were increasingly valued. Unlike many inventors who emerged from informal experimentation alone, Benz's early trajectory was shaped by structured learning and parental encouragement. His mother's insistence on education ensured that his curiosity was directed into formal training rather than remaining a hobby. This foundation placed Benz firmly on a path toward engineering long before the idea of an automobile had taken shape. Karl Benz entered formal education at a young age and progressed quickly. At just 15, he enrolled at the Karlsruhe Polytechnic at a time when engineering education was becoming more rigorous and mathematically grounded. His studies focused on mechanical engineering, encompassing subjects such as thermodynamics, machine construction, and physics. This education gave Benz something critical: a systematic understanding of how energy could be converted into motion. He learned not only how machines functioned, but why they behaved as they did. This theoretical grounding distinguished him from many contemporaries who relied primarily on trial-and-error experimentation. Benz was particularly interested in engines and power generation. Steam dominated industrial power at the time, but Benz saw limitations in steam engines, especially for small, mobile applications. Their size, weight, and complexity made them ill-suited for personal transport. This realization did not yet translate into a clear alternative, but it shaped his long-term thinking. Despite his technical strengths, Benz struggled financially after completing his education. Engineering knowledge alone did not guarantee stability. Still, his academic training provided resilience. He approached problems analytically, breaking them into components rather than abandoning them when faced with setbacks. This methodical mindset would later prove essential in navigating repeated failures. Benz's early professional life was marked by instability. He launched several engineering ventures, most of which failed due to limited capital, weak demand, or immature technology. These failures were not dramatic collapses, but slow, discouraging setbacks. Businesses closed, debts accumulated, and confidence eroded. What distinguished Benz during this period was persistence rather than sudden innovation. He continued refining engine designs even when commercial success seemed distant. His focus remained on internal combustion engines, which he believed held greater promise than steam for compact applications. Financial pressure was constant. At times, Benz lacked resources to continue experiments. Equipment had to be sold, workshops abandoned, and projects delayed. Yet he did not abandon his central goal: developing a reliable engine capable of practical use. These years shaped Benz's character. He became cautious, detail-oriented, and disciplined. He learned that technical success alone was insufficient without economic viability. This understanding later influenced how he approached commercialization, patents, and production. Rather than viewing failure as evidence of impossibility, Benz treated it as incomplete progress. Each attempt clarified technical limitations and market realities. This long period of struggle was not a prelude to a single breakthrough, but an essential phase in developing the resilience and clarity required for lasting innovation. A turning point in Karl Benz's life came through his marriage to Bertha Ringer. Bertha was not merely a supportive spouse, she was an active partner in Benz's work. She believed strongly in his ideas, often more strongly than he did himself during periods of doubt. Bertha contributed financially, using her dowry to support Benz's experiments when other funding sources were unavailable. This support was not symbolic. It directly enabled continued development at moments when projects would otherwise have ended. Equally important was Bertha's practical insight. She understood that invention required demonstration, not just design. Her confidence in the automobile's potential contrasted with Karl's cautious temperament. Where he hesitated, she acted. Their marriage provided emotional stability during prolonged uncertainty. Benz worked methodically but often pessimistically. Bertha counterbalanced this with determination and confidence. This partnership created an environment in which sustained innovation was possible. The significance of Bertha's role would later become visible to the public, but its foundation lay in these earlier years. Without personal stability and material support, Benz's work might never have progressed beyond isolated experimentation. Karl Benz's journey toward the automobile was defined by a sustained and deliberate commitment to the internal combustion engine. At a time when this choice carried significant risk. During the mid-19th century, steam power dominated mechanical thinking. Steam engines were proven, widely understood, and already integrated into industry and transportation. By contrast, internal combustion engines were experimental, unstable, and largely untrusted. Benz nevertheless believed that steam was fundamentally unsuitable for personal road transport. Steam engines were heavy, required long warm-up times, and depended on complex boilers and water systems. These characteristics conflicted with the idea of an independent, easily operable vehicle. Benz envisioned a machine that could start quickly, respond immediately to control, and operate without constant supervision. His focus shifted toward gasoline-powered engines, which generated power by igniting fuel directly inside the cylinder. This approach promised compact size and higher efficiency, but it introduced new challenges. Fuel-air mixtures were difficult to regulate, ignition systems were unreliable, and engine vibration caused frequent mechanical failure. Progress required solving many small problems rather than achieving one dramatic breakthrough. Benz worked incrementally. He refined carburation methods to control fuel delivery, improved ignition timing, and strengthened engine components to withstand repeated explosions. His engineering notebooks show a steady evolution of ideas rather than sudden innovation. Each design improved reliability slightly, bringing the engine closer to practical application. This persistence was critical. Benz was not chasing maximum power or speed. His objective was consistency. A vehicle engine needed predictable behavior, manageable output, and repeatable performance. By focusing on stability rather than spectacle, Benz laid the groundwork for an engine suitable for everyday transport, an essential step toward the automobile. A defining moment in Benz's journey was his decision to design a vehicle around the engine rather than adapting an existing carriage. Many early inventors attempted to attach engines to horse-drawn vehicles, inheriting structural limitations and inefficiencies. Benz rejected this approach. He recognized that mechanical propulsion introduced forces entirely different from animal motion. Engines produced vibration, rotational torque, and continuous power. A vehicle designed for these forces needed a dedicated structure. This realization led Benz to conceive a purpose-built machine in which every component served mechanical movement. The result was a three-wheeled configuration. While unconventional, it simplified steering and reduced mechanical complexity. At the time, effective steering systems for four-wheeled vehicles were difficult to implement reliably. The three-wheel design allowed Benz to focus on propulsion and control without introducing unnecessary risk. The chassis was lightweight yet rigid, constructed to support the engine while minimizing stress. Power transmission used belts and chains to transfer rotational motion to the rear wheels. Braking and steering systems were simple but functional, prioritizing reliability over refinement. This integrated design philosophy distinguished Benz's work from earlier attempts. The vehicle was not a carriage with an engine, it was a machine whose identity was defined by mechanical power. This shift from adaptation to integration marked a critical advance in automotive engineering. By 1885, Benz had assembled a working vehicle that embodied his engineering principles. The Benz patent motorwagen combined a gasoline-powered internal combustion engine with a purpose-built chassis, steering mechanism, and drivetrain. It was capable of moving independently on public roads under its own power. The motorwagen was modest in performance. It traveled at walking speed and required careful operation. Yet its significance lay in reliability and repeatability. The engine could be started, controlled, and stopped with intention. The vehicle could sustain motion without external assistance. These qualities defined it as a practical machine rather than a laboratory experiment. In 1886, Benz secured a patent for the motorwagen. The patent did not merely protect a device. It formalized the concept of a motor-powered road vehicle. This legal recognition was essential. It established the automobile as a distinct technological category and protected Benz's work from immediate replication. Importantly, Benz did not initially pursue mass production. His focus remained technical validation. He continued refining components, addressing weaknesses, and improving usability. The automobile at this stage was functional but fragile. Benz understood that long-term success required durability and public trust. The motorwagen represented the culmination of years of disciplined engineering. It was not the result of sudden inspiration, but of accumulated problem-solving. With it, Benz crossed the threshold from experimental inventor to creator of a new transportation system. Despite completing a functional automobile, Benz faced a final challenge: public acceptance. Technical success alone was insufficient. The automobile needed to prove itself beyond controlled conditions. This validation came through a practical demonstration rather than formal presentation. In 1888, Bertha Benz undertook a long-distance journey using the motorwagen, traveling over 100 kilometers. The journey exposed mechanical weaknesses, fuel supply, braking, and ignition, but also demonstrated resilience. Bertha addressed problems as they arose, sourcing fuel from pharmacies and making on-the-spot repairs. This journey transformed perception. It showed that the automobile could operate independently over extended distances and serve real-world needs. The demonstration was not planned as a publicity event, yet its impact was decisive. Skepticism gave way to cautious interest. Following this validation, demand increased. Benz began producing vehicles commercially, refining designs, and expanding manufacturing. Recognition followed gradually as the automobile transitioned from novelty to utility. Benz's journey illustrates how transformative technologies emerge through persistence, integration, and proof. His success was not defined by a single moment, but by sustained alignment between engineering capability and human need. By demonstrating that mechanical power could reliably replace animal transport on roads, Karl Benz completed the transition from idea to institution, establishing the foundation of modern automotive mobility. At the heart of Karl Benz's automobile lies the internal combustion engine, a machine designed to convert chemical energy into mechanical motion in a controlled and repeatable way. The fundamental principle is straightforward. Fuel is burned inside a confined space, and the force of the resulting expansion is used to move mechanical components. What made this principle revolutionary was not its novelty, but its application to personal transport. Fuel, typically gasoline, is mixed with air in a precise ratio. This mixture enters a cylinder where it is ignited. Combustion rapidly increases pressure, forcing a piston to move. This motion is linear, but through mechanical linkage, it is converted into rotational movement. Repeating this cycle continuously generates usable power. Compared to steam engines, internal combustion offered several decisive advantages. It eliminated the need for boilers, water reserves, and long warm-up times. The engine could start quickly, respond immediately to control input, and operate with fewer support systems. These characteristics made it suitable for compact, mobile applications. Benz's achievement was not inventing combustion itself, but stabilizing it. Early combustion engines were unpredictable and prone to failure. Benz focused on consistent ignition, controlled fuel delivery, and mechanical durability. His engine was modest in output but reliable in operation. This reliability was essential. A vehicle engine needed to perform predictably under varied conditions, not merely function in ideal circumstances. By grounding his design in controllable combustion rather than raw power, Benz established a principle that would remain central to automotive engineering for over a century. The effectiveness of the automobile depends on coordination among multiple components. In Benz's design, the cylinder houses the combustion process. Inside it, the piston moves back and forth as fuel ignites. This motion connects to a crankshaft, which converts linear movement into rotation. Fuel delivery was handled through an early carburation system, regulating how much fuel entered the engine. Too much fuel caused inefficiency and fouling, too little prevented ignition. Ignition itself relied on electrical sparks, timed precisely to initiate combustion at the correct moment in the cycle. Once rotational motion was produced, it needed to be transmitted to the wheels. Benz used belt and chain drives to transfer power efficiently. These systems allowed flexible routing of motion while absorbing vibration. Although simple by modern standards, they were effective and maintainable. Equally important was exhaust management. Spent gases had to exit the cylinder efficiently to allow the next cycle to begin. Poor exhaust flow reduced power and increased mechanical stress. Benz addressed this through careful timing and component placement rather than complex mechanisms. What distinguished Benz's approach was balance. Each component was engineered not for maximum performance, but for compatibility with the rest of the system. Power, reliability, and simplicity were treated as equally important. This systemic thinking allowed the automobile to function as a cohesive machine rather than a collection of parts. Beyond the engine, the automobile required a structure capable of supporting mechanical motion while remaining controllable. The chassis provided this foundation. It carried the engine, absorbed vibration, and distributed weight to maintain stability. Benz's three-wheeled design simplified steering. A single front wheel pivoted to change direction, controlled through a mechanical linkage. This reduced complexity and minimized failure points at a time when reliable steering systems were difficult to engineer. While later automobiles adopted four-wheel designs, the principle of mechanical steering control remained consistent. Braking was equally critical. Early automobiles used simple braking mechanisms acting on wheels or drive components. These systems were rudimentary but effective at low speeds. Benz prioritized predictability over stopping power, ensuring that braking behavior matched vehicle capability. Control systems were direct and mechanical. Throttle input regulated engine speed, steering adjusted direction, and braking reduced motion. There were no electronic intermediaries or automated systems. The driver's actions translated immediately into mechanical response. This directness reinforced trust and allowed operators to learn vehicle behavior quickly. By integrating engine, chassis, steering, and control into a unified system, Benz created a vehicle that could be operated reliably by an individual. Control was no longer external, managed by animals or tracks, but internal, governed by human input and mechanical response. The technical legacy of Karl Benz's automobile lies not in specific components, but in architectural logic. Modern vehicles differ greatly in materials, efficiency, and sophistication, yet the fundamental structure remains recognizable. Internal combustion engines still convert fuel into motion. Power is still transmitted through mechanical systems. Steering, braking, and control still mediate between driver intent and vehicle behavior. Over time, improvements addressed limitations Benz encountered. Multi-cylinder engines increased smoothness and power. Advanced transmissions optimized speed and efficiency. Suspension systems improved comfort and handling. Electronic controls enhanced precision. Yet these advances refined the original framework rather than replacing it. Benz's most enduring contribution was demonstrating that a self-contained mechanical system could reliably provide personal mobility. He aligned engineering capability with everyday human needs. The automobile became a platform for continuous improvement rather than a finished invention. This legacy extends beyond technology. The automobile reshaped urban planning, commerce, labor patterns, and social life. Its technical foundation enabled economic systems built around mobility and access. In technical terms, Benz's automobile succeeded because it treated transportation as a systems problem. Energy conversion, mechanical motion, control, and human interaction were integrated thoughtfully. By grounding innovation in reliability and usability, Karl Benz established the blueprint for modern road transport, one that continues to evolve while remaining rooted in his original engineering principles.